Hello, everyone. I would like to welcome you all to our the second phase of our workshop and session presented by Dr. Aman for the demonstration of the fog and IoT environment simulator. As mentioned before, Dr. Aman Singh is the head and director research innovation in ERIC, Spain, and USA. In this workshop, we will give hands-on experience on the simulator to model and simulate scenarios and to optimize the resources in the Internet of Things environment using edge and fog computing environment. Dr. Aman and Dr. Salil, they will demonstrate a practical demonstration. I would like to welcome them in this our second session. The first session was very informative. Thank you all, and the floor is yours, Dr. Aman.
Thank you very much, Dr. Saba and his associates for giving us this chance for this wonderful opportunity. So very quickly we'll be starting. I think we discussed about us, Team Eric, AIDA Labs. Next slide. Yeah, so we had a brief discussion about just a quick revision for the new candidates. If someone has joined new, so we are in the Engineering Research and Innovation Group, which is founded and sponsored by various academic universities and IT industries from Europe, North America, and other continents. So we have our centers in Spain, USA, Mexico, and Angola, and multiple centers will be opening very soon. And we are working in various disciplines: CSE, IT, biomedical, advanced sciences. Our research areas are artificial intelligence, blockchain technology, fog, IoT, cloud computing, wireless communication, cybersecurity, and computation sciences. Uh, as I'm leading the team, they have already discussed we have around 30 plus members in our team, which are led by Daniel and Rafal. And our international research collaboration is around the world: US, Canada, UK, France, with multiple universities. And as our plan was having two kind of workshop, basics as well as advanced, we already have our basic workshop on 30th of October, which is a wonderful audience, and we planned it in a way and try to cover all the theoretical concepts related to edge computing and resource management. In our phase one, we discussed about fog computing, what is cloud, how is it different from fog, and what are the different research challenges, how we can manage resources in fog computing. Then we discussed about summary of various approaches to resolve resource management issues in fog computing. Then we had some scope of work for master and PhD students. If someone has already noted that, that's great. They can ask us through email their queries if they have started working on those topics. And then we discussed about open issues and main challenges of resource management in fog computing. So today we'll be having the advanced training, and I hope that pretty much all of you has very basic understanding about how this fog computing works. And now we'll have a practical overview of this toolkit, which is helping the researchers for modeling and simulation of resource management techniques. And whether you're working in IoT, edge, fog, all this kind of work has been well simulated by IFOGSIM Cloud. So we'll give you the basic overview regarding that, how is to install it, and then we'll provide you the details of fundamental classes, which are very important. And then we'll discuss and demonstrate the applications, case studies, few case studies related to research, and then we'll provide the insight of the graphical user interface for building the network topologies. So after phase two, Salil, please hand over to you, all yours. Good luck. Please start with the practical demonstrations.
Okay. Thank you, sir. Am I audible to everyone? Voice is coming?
Yes, you are audible.
Okay. Thank you for confirming. So in phase one, we have already seen the basic concepts, that what is fog computing, what are resource management issues, and we have also given various problem definitions to the probable candidates. And I hope it was really helpful for them, and they might be working also, and they have also started with the literature on those particular topics. So today's training is all about the practical exposure of that, I'm picking one toolkit, that is IFOGSIM, which could work on the fog computing or edge computing environment. So IFOGSIM is contributed by the lab of Dr. Rajkumar Goya and Harshal. So they are the prime contributors of this. I will also show you a link from where you can download IFOGSIM toolkit and what are the various other resources you might get from that GitHub link. So first of all, I'm starting with the basic of IFOGSIM, that what IFOGSIM is. The name itself is self-explanatory, that it is the simulation environment or the simulator which will help us to model various case studies or various environments for our experimentations related to fog computing. So, in order to enhance the innovation and development which may require the fog computing environment, we preferably go with IFOGSIM. So, it helps us to explore what? The application designs and the resource management policies. So, application design, we can design any scenario. We can go for any application. It could be smart city, it could be smart grids, or smart healthcare system, or internet of medical things, whatever it is in relation to IoT application. Those designs we can go with the IFOXy. Moreover, it can also help us for application and task placement, migration, and consolidation. So whatever we have discussed in phase one, practically it is possible to implement them. And I will be showing you two case studies which are already given by the contributors of this work. The case studies are for EEG game, and the second one is on the basis of intelligent smart surveillance system based on the cameras. And the connection of cameras are there, and through that we are able to handle, or we are able to see how we can manage various tasks or various policies which are there to embed with. Now, if I talk about the iFox, see why the requirement was there for the simulator. In order to modulate or in order to formulate the IoT environment as a test bed, it is very much expensive. It is expensive, and on the real test bed, if you are working, it will take a lot of resources of yours. So we definitely need some virtual environment where we can model the things, and we can also see what are the approximate results that could come, or when we are able to deploy the application in the real environment, what are the possible chances that it will be deployed successfully and the fog computing layer is working perfectly well in that scenario. So all these things are coming into the mind when the contributors are gone with IFOGSIM simulator. So it will help us to perform the simulation of resource management and application scheduling policies. See, the application scheduling also was one of the problem definition that I discussed in the last training. I hope the people are having reminder of that. So the same thing we will be seeing here in IFOX. Now, coming to the various applications, it will help us in respect of what? It will help us to implement various resource management policies that I already told you. And we can go with various, performance metrics which can help us to evaluate the things like latency, energy consumption, network congestion, and operational cost. So based on this, we can evaluate our performance, we can evaluate our experimentation work, and we can judge what advancements or what improvements we need to do with respect to the application deployment. Not only this, the contributors of IFOGSIM has also given us the performance metrics like the network use and the perceived latency. So network usage is one of the important factors. Perceived latency is more or less is similar to the normal latency that I already discussed. But the network usage is going to be, a very important parameter, because less usage of network, it means you are going with good application placement policy, or you are also managing the QoS requirements that cloud and fog computing are agreeing to. It can also simulate the edge devices, cloud data centers, and network links to measure the performance metrics. So I will tell you the required classes which are there in the Java that we can extend or we can override the methods of them so that we can come up with something which is as per the requirement, or we can customize it. So I will show you the related case studies, and you can alter them as per your requirement. That is not a fixed thing. I will show you something which is in the form of a template, and that template is customizable. So it will make sense for you, or it can help you further for your experimentation work. So from this slide, we are inferring that, okay, these are the various performance metrics, or these are the various applications that are being handled. Now, the major application module considered for IFOGSIM will consist of sense, process, and actuate model. So what sensors will do? Sensors will read or sense data for you. Then there is a processing module, maybe the data processing we can say, and then the actuators which are there in the IoT layer can behave accordingly. The major difference between sensor and actuators will be, sensors uh, will take the physical characteristics, and then it will be converting that into electrical signals, whereas actuators will take the electrical signals and then they will perform something as a physical attribute. The example of actuators we can say like motors or heaters. They emit heat, or the motor is also working in the same manner. So they are working as differently as the sensors are working, but both are having their own significance in the IoT. The sense, process, and actuate model will work, and the entire processing that we are going to do will be on the fog layer. Moreover, apart from the performance metrics, or apart from this sense, process, and actuate model, it also gives us the simulation recipe and the case studies to model an IoT environment. So that is the major thing. And we can also go with the physical topology creation, because whenever we are designing any network, the topology is going to play a very important role. And as per the architecture of fog computing, we know we can formulate the topology in three layers, like the IoT layer, fog layer, and the cloud computing layer. So we'll come to that. Now, the first point, the first practical demonstration I'm going with, you can simply go with the installation first. So the first thing is you need to go with this link, cloudbus.org, which is managed by the Cloud Computing and Distributed Systems Laboratory, University of Melbourne. And I already mentioned about Dr. Rajkumar Goya, who has great significance, or the main contributor in this field. And his team is also working rigorously on improving the IFOGSIM versions. Right now, IFOGSIM 2 is also published. So, based on your requirements, like let's suppose you are going with something mobile agents, or the mobile fog computing, if you are going with a mobile edge computing, you are going. So, you can go with IFOGSIM 2 also. That is more advanced. But even the IFOGSIM is yet to be explored. Many researchers are working on that part. So there are various classes they have already given to us, which we can extend and we can make use of that. So we can go with the inheritance model, we can extend them, and whatever derived class you are making, you can also add on the new methods, or you can override the existing methods as per your requirement. So the first step of installation I'm going with, you need to go to cloudbus.org fog. If you write this URL, you will be finding it. And I'm just marking here. You need to go to this particular part. Download IFOGSIM here. If you click on that, you will be redirected to the GitHub page, github.com /IFOGSIM. Now here you will be finding a link of clone or download, and then you can download the zip. If you download the zip, it will be around 30 MB or around 28 MB that you can download. When it will be downloaded, you need something in the form of the Java ID. See, the Java IDs are coming in many flavors. Like you can go with Eclipse, you can go with IntelliJ, you can go with NetBeans also. There are so many variations available. I always prefer Eclipse, which is I'm having a lot of expertise in Eclipse, so I'm going with that only. If you prefer NetBeans, you can go with that also. IntelliJ is also there, you can go with that. So there are various IDs available which can run your JDK, JRE, and your Java based coding. So you need this Java IDE if you want to work with IFOGSIM, because all the classes are modeled in Java language only. So you on Google, if you simply type the eclipse.org downloads, you can go with the latest version of Eclipse. If you're working on Mac, you can download that version, or Windows or Linux, whatever is suitable to you, you can go with that. So here I'm highlighting the Windows 64-bit environment because I'm working on Windows. So you download it, you install it. So once your Eclipse IDE is ready, you can go ahead. See, after downloading, you will be getting the IFOGSIM master.zip. This is the zip file. And then we have Eclipse also. So you need to, unzip them. The folders will be created. Eclipse is already installed if you have gone with that the previous slide. So Eclipse is already installed, but still if it is not installed, you can unzip the Eclipse zip folder also and you can install it. But iFoxim master folder must be unzipped because it will be required in the path. Once you have done that, you can go with the exploration of iFoxim master, where you'll be finding these folders like jars, output, results, src, topologies, and these two files. So these are the contents of your iFoxim. So once we verify that all the folders are available, we are good to go with the creation of a new project. So after that, you will open your Eclipse workspace. You can go to file or you can go to the new project. Otherwise, in the package explorer itself, there is option available, create a Java project. You can click on that and then you do the things which are required to make any project. You will give your name here, the project name. It could be any name. Let's suppose you are giving the name IFOG demo. That name you can give. And afterwards, you can untick this option, use default location. Don't go with this default location. Untick this option, and then in the location, you will simply copy and paste the location of your iFoxim master. Wherever your folder will be unzipped, that path you will take and you will paste here. And once you are pasting it, your Eclipse will recognize that folder, and then you can click on the next button. When you click on the next button in the package explorer, you will be finding iFoxim test source like this. And just after this, if you click on the source, you will be finding various files which are related to iFoxim. Now I'm just minimizing this, and this type of workspace you will be finding. So this is iFoxim test source, where you can see the CloudSim packages are available. And we have also the fog related packages which are visible to us. So I will come to these folders in the next couple of slides. So this view will make sure that your iFoxim is correctly installed. Now let's discuss about the architecture of fog computing in iFoxim. We know the normal architecture of fog computing, but the architecture of fog computing in relation to iFoxim, we must know. We should know that how the architecture is designed with respect to the simulator. Then only we can understand the classes, the probable classes which are available. Then only we can understand. Now, if I come to the bottommost layer, it is IoT sensors and the actuators layers. So, it is the bottommost layer which interact with the real world, and they are the sources or the sink of the data. So IoT sensor will act as a source of the data for the applications and are distributed in various locations. Their prime task will be to sense the environment and emit the observed values. It will carry on with the observed values. The sensors could be of any nature. I'm not giving any specific name here. They are the generic sensors which are working. And once the observed values are there, they are transported to the upper layers, and who are helping us here? The gateways will connect one layer to the another layer, and the sensed values are transported. Similarly, The actuators will also operate at the bottommost layer of the architecture, and they are responsible for controlling a mechanism or system. See, when I say controlling a system or mechanism, it means they are working as an output of physical attributes. So, whatever things are sensed by the sensors, they are being processed at the upper layer, and maybe later on IoT actuators are working as per the processing which is being done. So the same model is coming here again. It is like sense, process, and actuate. So this is the bottommost layer of the architecture. Now, actuators are usually designed to respond to changes in the environments, so that are dictated by the applications. So the applications are already deployed in the fog layer. They will process it, and whatever sensors have initially received the information, maybe according to that, actuators need to behave, or they can do some physical attribute changes. So this is how the bottom layer is working. If I talk about the input process or how to sense the data from the environment, we have so many other things apart from sensors like smart readers, cameras, even microphones are also there, collectors are there. So they all are the input devices, I would say, because they will detect the information from the environment, and then it will be transported to the upper layer. So sensors is one of the thing that you can say, okay, fine, but apart from that, these things could also come in the IoT layer. Now, any device belonging to this, they will have some data emission characteristics like intermission time or size of the data chunk emitted. See, it's all about data. How the data is being inferred, how the data is being taken into consideration, or what is the intermission time, everything. These two parameters are going to be, the major parameters of what I just discussed with you. These devices, the input devices, which I'm talking about. So this was the bottommost layer, and now we are moving ahead with the fog devices. See, the fog devices, the next part of the architecture will come into picture. They are the any element in the network which are capable of hosting application modules. As we know, we are simply replacing the cloud layer with the fog layer to some extent. I'm not saying fully, but to some extent we are replacing it. So the fog devices are fully capable to host the applications. This is what the intention is. And how the fog devices will take the data from the sensors or the input devices, this is done through the gateways. Cloud devices will also include the cloud resources that are provisioned on demand from geographically distributed data centers. So sometimes we say it fog devices as foglets. The foglets is the another terminology, and they are the mini data centers also. As we have the data centers in cloud, we have the mini data centers in the form of foglets or fog devices as well. So what the fog device layer will do, it will, it will try to cover the resource range stretching from the edge devices to the cloud also. So the fog is working as the intermediate layer, and it is responsible to cover up the all resource requirement starting from the edge layer to the cloud layer. So devices are also arranged in the hierarchical topology, as we know that, because then only the streamline flow of data is possible, and they are working like a parent-child pair. So when I say hierarchy, they are working like one of the node is the parent node, and then we have the child nodes as well, which are working in tandem. So the application module which is running on the fog device is responsible for processing the data. So we can deploy any machine learning algorithm or deep learning algorithm which is going to sense or which is going to acknowledge the data, and maybe it can generate the responses in the form of how the system should behave or the nature of the application we are working with. So for an instance, let's take an example here. The smart cameras are recognizing the streams of the data from a particular area. That data or that input images are directly transported to the fog layer. Then we have some machine learning or deep learning based algorithm working there, maybe in the form of VGG16 or VGG19. which is recognizing the collection of images, and maybe it is giving us some regions of interest. Maybe some region of interest are there. Let's suppose someone is violating the rules of traffic. So, see, the manual intervention is not possible. Manually, how we can judge? Because there are so many, time frames. There are so many images which are keep on getting collected. So it is just like a video processing. So from the video processing, we have the frames, and definitely we need some deep learning mechanism to work on that. So we can deploy that deep learning module on the fog computing layer, and it can help us to recognize something which is not as per the law, right? So it will process that collection of images, and then it will return back the responses, and that responses are given to the IoT layer. So maybe if someone is violating the rules, the whatever tickets we can generate against that person, and the tickets are automatically sent. So this is one of the simplest application we can think of. Or maybe we are working with smart parking system also. So where constantly the set of cameras are recognizing a set of area, and that area is having the vehicles parked, and it is constantly telling us how many areas are left, and so and so. So that processing is also being done on the fog devices. So the fog device at the architecture level will play a very important role here. Then we have IoT data streams also. So the data streams is the same thing I just discussed with you, the sequence of values which are being emitted by the devices from the next layer of the architecture. So they are again emitted by the sensors, and they are recognized by the fog devices. Definitely on the fog layer, we have a monitoring layer as well. So that monitoring layer is the sub-layer there, which will keep track of the resource usage, power consumption, and the availability of sensors, actuators, and fog devices. So everything is being regulated by the monitoring layer. So that information is required to be updated with a definite interval of time. Otherwise, there will be a problem. So that monitoring layer is also modeled in the IFOGSIM architecture. Now, coming to the resource management part, which is our area of concern. So that is also modeled in the form of classes. So what is the role of this component? It will, manage resources of the fog devices in such a way so that the application level quality of service constraints are met, and there is less resource wastage. See, in terms of computing, we always prefer that a particular application, a particular task is taking less time for its execution, or it is taking less computing power. So our prime purpose is always to reduce the resource wastage. So that part will be managed under the resource management set of classes. So everything we need to model first, then only we are able to monitor the things, or we can manage the things properly. So that is coming under the resource management part as well. So it will also keep track of the available resources, just like it can create a resource queue or a set of resource pools which are available or which are allocated. Or we can also work like a resource graph, in which we can simply say, or we can simply visualize how many resources are still under usage, how many resources are still, free. We can work with that. Then at the end, we have the application programming models as well, which is the actual deployment of the application layer, and they are also known as distributed data flow model. Distributed data flow. Why? Because I already told fog is decentralized and distributed. So how the application is deployed, that is being taken care by the application programming models. So they construct one DDF model from where we can visualize how the application is being distributed. So it is like the collection of modules because it is distributed, and it constitutes the data processing element. So whatever data is generated by module I, it may be used by the module J. So we can consider like the application is divided into modules M1, M2, M3 on various distributed regions. And maybe from one region, when the module 1 is completed, that output will be used by the other region which is having module 2 deployed. From module 2, it is now moving to module 3 and so on. Or maybe the sequence is not followed. It could be working like in a random order. Some other module is getting completed first, and maybe that output is required by some other module. That is a possibility. So it is all working on the DDF model part, and this distributed data flow will make sure the data dependency also, that which module is dependent on the other module. But if it is not dependent, then it can work like a random modules. So whatever we just discussed, this is the illustration of that. The bottommost layer, IoT sensors and actuators, fog devices. Then we have the data streams. In the infrastructure monitoring, we have the monitoring of everything, not only the resources in terms of fog nodes. Here the monitoring being done for the data which is getting published, or the available fog devices, or the available sensors or actuators. Then we have the performance prediction, and simultaneously a knowledge base is also getting formulated. Then the resource management part of architecture is coming, where we have the resource provisioning. Resource provisioning means the resources that we are already occupying or giving to a set of tasks. And maybe when the tasks are changing, we are going with the dynamic scheduling or static scheduling as well. And application models are there. I already discussed about sense, process, and actuate model. Under this, we have the stream processing as well. So stream processing is like a subcategory of sense, process, and actuate. And at the top, you can see we have various varieties of IoT applications. Maybe it is industrial IoT, or smart farming, or maybe smart waste management, smart city environment. It could be anything which is related to IoT. This is the architecture. So models, the sense, process, actuate model, I already discussed. I'm not going to discuss it again. Now, the next part is the stream processing model, which will have the network of application modules running on the fog devices. So the network of application modules will keep on doing what? They will keep on processing the data streams which are being emitted from sensors. So once this sense, process, actuate model is working, inside that model, always the stream processing model is working. This is for sure. So it is like the subset of the complete set. So it will make sure whatever data is being generated, it is constantly mined, and we are generating the hidden patterns out of which are the point of concern for us. So the noting point here is stream processing model is a subcategory of sense, process, and actuate model. So in the IFOGSIM architecture, these two models are working. Now we are coming closer to the set of classes also which are available in the implementation. See, IFOGSIM is totally built on CloudSIM. Various classes are there which are being taken, and they are, extended, or you can say they are modified in a way so that it can work in the fog or edge environment. But yes, it is built on the CloudSIM. And these are the fundamental classes. We should remember these classes. These are very important classes on which we will be working. Module placement mapping is there. Module mapping, controller, fog device, module placement, app edge, app module, app loop, and application. I will discuss them one by one. And these are the physical topology classes: fog device, sensor, physical topology, and actuator. So these are the physical topology classes of IFOGSIM. So let's go ahead with their illustrations or their descriptions. So fog device is one of the important class of physical classes. So what is this? It is going to handle the hardware characteristics of a fog device. So whatever attributes in relation to hardware related to a fog device will be handled by the fog device class. And whatever their connections to other fog devices, sensors, and actuators, that is also being handled by this. Moreover, it is the extension. I already told there are various classes from the CloudSIM, from where these classes are made. So we can think of like fog devices, the derived class from the power data center class, because this is the base class for this. So whatever the power data center based class is working in cloud, the same is being handled by here. So now we understood about the fog device very well. So we can relate also about the power data center in cloud sim. Maybe the audience is not having knowledge of cloud sim as of, but yes, we can relate from the fog device that what the power data center would be. So it is taking the attributes from this class and also having its own attributes. Moreover, the attributes I would like to say about it will be the memory, the processor, storage, size, uplink, downlink bandwidths. So these values we will also give while we are creating the physical topology. We will enter these values and accordingly we will make our fog device. Methods in this class will also define how the resources of a fog device are scheduled among the application modules running on it, and how the modules are deployed and how they are going to decommission on them. So there could be a chance that once the modules are deployed, further they are also moving to other fog devices, or maybe we have the module placement. So that is possible via these classes. Now the next class is the sensor class, very important. From the IoT layer only will be emitting the data. So for emitting that data, you need to model the sensor class as well. So the instances when you will be creating from sensor, you can generate various types of sensors out of it. So if I say instance means the object of the sensor class. So if one object of sensor class would be generating one type of sensor, the other type of sensor class would be generating the other instance or the other sensor type. So various types of sensors we can generate from the instances of the IoT sensor. So again, you can directly create the object. You can pass the suitable parameters a sensor would take, and accordingly you can work with that. Similarly, we have the actuator class. So this class models an actuator by defining the effect of actuation. So here again, we can work with the instances, various instances, and we can generate various type of actuators out of it. And there are various methods which we can override to get the customized effect of actuation. Am I audible? My voice is coming.
Yes, we can hear you. Mr. Savil, can I ask you about something? You
Yes.
said sensor class can actually create a lot of sensors. Can it create industrial sensor types?
Yes. See, we need to give different types of values. So whatever the industry sensor values will be, you will be passing that in that method, the method belonging to the sensor class, and we can generate.
So we need to define the values. I mean, it won't be simulated.
We need to give the values.
You mean the expected values based on a particular type of sensor?
Yes, yes. Then only it will be.
And how about field instruments? Can we simulate field instruments here?
No.
Oh, no. So it's only the sensor part and actuators part.
Actuator part, yes.
Okay, thank you.
Okay. So moving further, then we have the tuple class also. So tuple is a very important role here. It plays a very important role. Why? Because it will act as the fundamental unit of communication. So when we have the sensors or the fog devices or maybe interconnection of the fog devices, that is being handled by the tuple class. The tuple class will also play a very important role here. Moreover, it is the derived class of the cloudlet class of cloud. So what the cloudlet class will play the role, the same role is being handled by the tuple class. So the tuple is characterized by its type and the source and destination of the application modules, and it requires the million instructions as one of its parameters. So the million instructions is the processing requirement, or we can say MIPS also, million instructions per second. In that form also we can say, and the length of the data encapsulated in the tuple. So tuple will help us to formulate the connection among the various entities in fog computing. Then we have the higher level classes like application class. Application class is give the application design of the IFOGSIM, which follows the DDF model I already discussed in the form of a graph. So, and in the application itself, it will be formulating the modules which are there for the application and how they will be working. And this is the application is working in between. So application will regulate the response should not be higher because latency is one of the important parameter we need to manage. Latency could be as low as possible. So that is being tracked by the app loopers. So whatever the process control loops or whatever latency is being measured from one fog device to other fog device once the data is submitted from the sensor is being handled by the app loopers. Talking about what are the simulated services available in IFOGSIM, it is the monitoring service and the resource management service. The monitoring service I already discussed in the architecture part, where we have the monitoring layer. So that monitoring layer is modeled with monitoring service. So we have one very important method called execute tuple method, which will make sure the information which is being sent from the sensor is deployed is being sent to the particular fog device, which will execute this method and will make sure the result is coming. Then we have the resource management service in the form of application placement and application scheduling. Now, the application placement service, we will make sure there is a class called module placement, which will help us that from the application, whatever modules are being generated, so that module, how it is placed on a particular fog device or set of fog devices, it is being handled by the module placement class. Similarly, we have the scheduling also. So once the system is working, once these requests are constantly coming from the IoT layer, so maybe those requests are divided into the tasks, and then those tasks are required to be scheduled also. We have done in the previous workshop also, we studied about the task scheduling. So that task scheduling, if I go with the collection of task scheduling, it could be the application schedule. So this is one way looking into it, or we can have the couple of applications working simultaneously. So that also could be scheduled. That is the upper level scheduling. So in between the application, the task scheduling is also handled here. Now we are up to the application case studies. The very first case study is the latency sensitive online game. This is very interesting, case study they have given to us. So if I go with this, it's quite workable as it is augmented brain computer interaction game. So we might be aware of this that the gamer is going to wear the EAG headset, just like Windows 4S wireless EAG headset, and accordingly the brain concentration power will be recognized, and accordingly the player can play the game. So maybe you need to make a ring. The players will make a ring surrounding the target object, but that target object, whether you are able to hold it or not, it all depends upon your concentration power. Now the thing is how that concentration power is, computed, measured over the period of time, so that you can get your response on your device on which you are working. Maybe it will be smartphone only where the player is playing the game. How that response is coming back again and again. So that is the fog computing layer where the fog is coming into picture. That concentration calculator is one of the major application here to be working. So that latency sensitive online game case study is given. So what it does, the application performs the real-time processing of the EEG signal sensed by the EEG headset. So this is the IoT layer. You can think about it, and calculates the brain state of the user. And on the applications display, what you will be able to see, the players on a ring surrounding the target object. And primarily how this is going to be computed, it all depends upon the attractive force on the target in proportion to the level of its concentration. So higher the concentration is, higher will be the attractive force, and accordingly you are winning the game, or maybe you are closing the game also. So it will be estimated via alpha, beta, and theta bands of the player. So these are some computations which are being done under the concentration calculator. So to win the game, what a player should try, he should try to pull the target toward himself by exercising the concentration, and while the other players will be deprived. Are you able to make the other players deprive of that target? So that is the major thing which is going to happen in this latency sensitive online game. So this is the application model of that. See, for every application you are making, it is always advisable, please formulate the application model first. Because until unless you are not making the application model, you are not aware how that application will be deployed, how many fog devices will be required, how the fog nodes will be interacting. So that type of knowledge is required in the form of application model. So we can understand from here, the client, the EEG signals are being tracked through the sensor, and then we have the concentration calculator, which will constantly giving the answer of the concentration to the client on the smartphone. At the center level, we have a coordinator as well, which will keep on giving the information globally. Globally information means the information of other players as well. So that information is being tracked and is transported back to the client. So accordingly, client self state will be updated, as well as the global state is also updated. So the concentration calculator and coordinator are the two processings which are constantly happening here. Okay, so this is happening at the local level. When I say local level, it is at the player level which is playing it. And this is happening at the global level. So the application model is making sure local level as well as global level states are being updated. And they are updated and they are flashed on the display screen of the player. This is one information we need to formulate. And the other information is the requirements. So what is the EEG sensor requirement? The CPU length or the network length in terms of bandwidth. So sensor, player game state, concentration, global game state, global state update, self state update. So these are the other things which may be requiring the CPU length in terms of millions instructions per second as well as the network length. So initially we can fix these things and accordingly the overall latency will be computed or the energy consumption will be computed. Similarly, we can configure the fog devices as well, like the cloud virtual machine, Wi-Fi gateway, which will connect the fog layer with the IoT layer, the smartphone, or the ISP, Internet Service Provider gateway. And these parameters we can set initially, the CPU, RAM, and the power in terms of watts. That information we need to get. So this is the first case study, and I would like to show you the demonstration of this. So there is a very important folder you will be finding, fog.test.perfevl. So in this folder, you will be finding this vrgamefog.java. This is the file where all the methods are already overwritten. This is the VR game class. So we are making list of fog devices, sensors and actuators. Initially, the cloud variable is false, then the number of departments, number of mobiles per department, and the EAG transmission rate is also given. So this is the main function where the entire application will be running. We have a fog broker class as well. Fog broker class will take care of the scheduling part or whatever the resource requirements. This is the main application class I discussed with you. We will make the instance, and the create application method will help us to create the instance of this application class. Then we have the module mapping as well, and we call the create fog devices method. Similarly, we have the controller class as well, and we submit the application by passing the suitable parameters. Then the create fog device method will be overridden. You can see here I am generating the fog device by passing the suitable parameters. Then whatever resources are there, mobile or whatever GW gateway, we create the fog device, and these are the architecture level configurations. Then add tuple mapping will be required, mapping via the tuple as well as the edges. And finally, we can run this. So initially it will be creating the client on device, and this is the final outcome which could come in the form of delays and the energy consumption. Energy consumption at the cloud layer or the proxy server. The proxy server will connect the cloud layer with the fog layer, and this is the energy consumption values coming in terms of joules, and the tuple CPU execution delay in the form of milliseconds, and this is the total execution time of the application in terms of milliseconds. So this is one application, and all can study about these methods, the parameters they are taking to formulate the things. I highlighted the important or the major classes we need to study. and accordingly you can override it. These are, you can think about, they are like, the template classes right now. But when you are going with the application modeling, we can override this. Then we have the case study 2, intelligent surveillance through the distributed camera networks. So here the case study is focusing on the video streams which are being generated from a set of area through the cameras, and the requirements will be why we are making such applications, because of low latency communication, or we need to handle the huge volume of data or heavy long time processing. So video processing is not an easy task. So for that task, rather than we are moving to the cloud layer or we are doing everything on the edge, we are bringing the cloud, the fog layer, so that the video processing is being done in a short span of time and the responses are given back. And for effective object coverage, one important aspect of cameras we need to manage, that is pan tilt zoom, PTZ parameter. So it should require the low latency communication between the cameras and the set of cameras deployed in that area. Talking about the application model of this, we have the motion detection, object detection, object tracker, PTZ control, and the final user interface or UI which is working. So what is the role of motion detection here? This module will be embedded inside the camera only, so that it should be working like a smart camera. And it continuously reads the raw video streams captured by the camera to find the motion of an object. Once the motion is detected, the data will be sent to the upper layer. Similarly, the object detection is also there. We are looking for a particular object, it could be a vehicle. Then the object tracker, we can track the last location of the vehicle and so and so. Then the PTZ control, I already discussed the important parameter of any smart camera, which is to be taken care, and the final UI, which you will be making to see uh, the movement of the video streams. So this is the application model for this as well. As we can see, the camera will generate the raw video streams, and it is going to the motion detector, then it is going to the object detector, and then we have the object tracker, and finally we are going with the PTZ control. So for this also, we are giving the parameters of CPU length and the network length, and finally the configuration of sensor. So 1000 million instructions, network length in terms of bytes, and the average inter-arrival time in terms of milliseconds. The three parameters of evaluation the contributors of IFOGSIM have used, they are the average latency of control loop, the network usage, and the energy consumption. I would like to execute this. So here we have the number of areas we are working with. See, this is customizable. You can work with any number of areas and the number of cameras per area also. Then in the same manner, the module mapping will be done. The application class instance will be created, and we will also call the create fog devices. Whereas the fog devices creation is done here, as you can see, the overridden method of create fog devices will pass the suitable parameters. Then the loop is running as per the number of areas which are there, and we will keep on adding the area, because here we are not working for the single area, we are working on the smart city environment, so there could be a couple of areas we are working about or working on. So add area method is also given, where in the area we are adding the camera. Then we have further hierarchy. As I told, the hierarchical model we are using. We add the camera. Inside that camera, we have the sensor and the actuator. And finally, we are up to the fog device. So once the IoT layer part is completed, then the create fog device. With the computational parameters and the operating system level parameters we are giving. And then the DDF model. I already discussed about the DDF model where the tuples are required. So app module, app edge, and the tuple mapping will be done. So that the motion detector, object detector, or the PTZ control module, they all are linked up. We can verify here also the DCNS fog. These are the parameters, or the classes we have used, and these are the methods which are overridden. Then we can run it. So for a demo purpose, they have created this, and the values are coming. The execution time and the loop delays. Loop delays, I already communicated that at what particular time from motion detector to object tracker, the data is being sent. And from object tracker to the PTZ control, in what time the data is being sent. And this is the final energy consumption between the devices as well as cloud proxy server also. And finally, we have the network usage. Now the next thing is uh, how we can create the physical topology. As I discussed about physical topology also. So for generating the physical topology part, we can go to the GUI package. Let me just open that. Yeah. So org.fog.gui example, here you can go and you will be finding one file, foggui.java. When you click this, you will be finding a long list of code where various swing controls are available alongside with their action listeners. I will run this. You will understand why the action listeners or swing controls are given. We'll run it. It will give us a GUI form like this. Now here we can, frame the topology. Like you can add the fog device, you can add the actuator, you can add the sensor. If I click on add fog device, then you will give the fog device name, the level, 1 or 2, the value for uplink bandwidth, downlink, MIPS, and RAM also you can specify. Rate we can give, rate of MIPS we can give. Okay. So this is how it will be plotting the device on the canvas. We can generate a proxy server also. Some values. We can go with the sensor design also. This is the add sensor part. These are the values I was talking about. Suppose I'm generating the industrial sensor. Distribution type, normal, uniform, or deterministic. If you go with deterministic, then we will give a perfect value here. Otherwise, you can go with the uniform also. In uniform, you can give a range, minimum or the maximum. If you go with the normal one, then you will give the mean or the standard deviation part. Relates to sensor. This is my first sensor I have generated. The second sensor. So we can also go with actuator here. Let's suppose the name is, type is heater. This type of scenario is being formulated. We can combine them also via add link. So add link dialog box will show the available things on the canvas. So it is always advisable to connect your proxy server. One second. We can also make the cloud layer, cloud data center. And we can establish the link. This way, we can link also the things. So this is just the illustration I have given you. We can save this topology also, like save physical topology, and it is advisable to save the topology in the topology folder itself. So there is a folder also available, topologies here. This one. You can right click there, go to the properties, and from there you can copy the topology location. So once it is there, you can save it. You give your path here where you want to save. So once you're into the path, you can give the topology name. Like this. So at the background, we can see this is how the output is coming up. So once we close it, we need to refresh this folder. When we refresh it, you can see the demo topology is available. If you want to open it again, first advice, you need to open it with the JSON editor, because this is the JSON file. So go with the JSON editor. If JSON editor is not available, what we can do, we can we can add the plugin of JSON by going into the help and install new software in Eclipse. So when you click on it, you will be finding your entire GUI in this form. Nodes are there, and we have the links as well. I'm going to that part where the link is available. Yeah, here we are. So this is the link part. You want to see this in the form of a perfect tree view, then you can go to right click and then format. So when you click on format, everything will come in this way. The collection of nodes are available, and this is the link. I generated only one link, so only one entry is available. When you will be combining all, you will be able to see the entire thing. This is the perfect way to come up with. So when I close it, so this is your demo topology available. Now the next thing is how we can open it again. Once the topology is created, how we can open it again? This is the GUI. You run it again, the GUI file, and here you will get the option to open the saved topology. So this is the open the physical topology, and always have that path of topology where you have saved it. This folder. Again, I'm going to the properties part, taking the topology path. Again, go to there, enter the entire path, go to that folder, and this demo topology I'm opening again. You click on import file. It is open again. Similarly, I can open router topology. This is the router topology. You can see cloud, router, mobile 0, mobile 1, and these are the sensors or the actuators. Or maybe the other one, the copy of VR game the contributors have created. This is a VR game topology they have generated. The EEG headsets and the display. The display is on the smartphone. Mobiles, Wi-Fi gateway, ISP gateway, and then cloud. This is how it is working. I hope that topology part is clear. How you can generate the physical topology and what are the various methods or classes for various applications. So this is the snapshot view of everything that I have given. Just shown you practically. Yes, so here we have, until the conclusion part. So let me just go through the things we started with. We have successfully completed the practical overview of IFOGSIM. Basic overview I gave you, the application part, installation steps, the fundamental classes, and the application case studies, and also the insights of IFOGSIM GUI for building the network topology. One advice for everyone, one paper you must read on this one. Simulating fog computing application using IFOGSIM toolkit, written by Avasi and Abbas. Very good paper. They have given the code for various case studies like smart car parking system. They have given the code. They have also given the complete scenario, how we can generate it. See, the fog device, sensor part, actuator part, and this is the code snippet 1 that you will be writing in the main class. Then the code snippet 2 in relation to the same case study where the application part is given, and this is the topology they have formulated. Then the smart waste management system is also given. Given the scenario first, and then the code snippet. This is the application model. Application model is very important. Then you can start the code. See, almost they have given the entire code. So this paper is very helpful for the beginners. Then smart mining industry system. This is another scenario. The application model. See, the master module is taking the data from the gas sensors or the chemical sensors, and then the modules are available. Then sensing as a service, the unnamed area vehicles, UAVs, very trending topic nowadays. The application model is given, and the code I just discussed previously. So this paper will help you a lot. Okay, so people can note down the title of this paper: Simulating Fog Computing Applications Using IFOGSIM Toolkit, written by Avesi. So this paper you can download. Moreover, whatever we just discussed today, most of the part is given in this SPE paper, which is given in cloudbus.org. If you click on that, you will be finding this paper. Toolkit for the modeling and simulation of resource management techniques. So Harshit Gupta is the major contributor alongside Rajkumar Boya. This paper also you can go through. Very helpful. The installation steps I already discussed with you all. And the major classes, how to build the topologies and how to run the existing case studies, how to override the methods. So all that discussion is done. So I'm into my conclusion part. Thank you. If you have any query, you can go ahead.
Thank you very much, Dr. Salid, and thank you to Dr. Aman. And if the audience have any question, they can write in the chat or they can open their mic and ask a question.
If there is any query.
I don't think the audience have any question. Thank you, Dr. Salid, for this session. It was very informative, and thank you for the paper you recommended and the practical presentation. Thank you very much, and we'll see you inshallah soon.
Welcome.
Okay, thank you all for attending, and see you in the other sessions.